Hello everyone. Uh, Today we will see again principal stresses and planes. So in previous lectures we already learned when a member is subjected like tensile stress or tensile force and a member subjected to like direct stresses in two mutually perpendicular planes. So today's topic of discussion is a member subjected to a simple shear stress. When the shear stress act on a body, then we will find the principal stresses and principal plane. Before that, I would like to explain the principle of complementary shear stress. Now let's say this is a bar A, B, C, D having unit thickness. So if you observe, this particular bar is a 3D bar and having unit thickness. So thickness is 1. Now when this bar is acting a shear stress on this particular surface, so if I consider the shear stress tau over here on this particular plane AD, same shear stress tau is acting, and on this particular plane DC, tau dash is acting. Similarly, on AB face, tau dash is acting. Now when this shear stress is acting on particular plane, then it is equal, tau dash that is equal to tau. So how this can be analyzed through this principle of complementary shear stress. Now let's understand how this happened, tau equal to tau dash. Clear? So let's start of discussion. The force acting on this particular AB, because this is a shear stress. So force acting on AB due to this shear stress, so that will be the tau dash into AB, and thickness, unit thickness is 1. Clear? Similarly, if you observe, there is a tau dash, it is acting on CD plane also. So force acting on CD, that will be equal to tau dash into CD into 1. So these two forces, if you observe, as this tau dash is similar and length of AB and CD is similar, then I can say that the force acting on AB, that is equal to force acting on CD. Now when two similar forces are acting same intensity, but the nature, if you observe, it is an opposite direction, so this will trend to rotate the body. So this will form the couple. When two equal and opposite forces are acting on a body, then it will form a couple. So I would like to evaluate the moment of couple. So first we will see the moment of couple due to one of the force. Now here I will consider this force. So this force, that will be equal to tau dash into AB into, now how we evaluate the couple? Distance between these two force. So I will consider distance between these two force which is acting on AB and CD, it is AD. So here I will consider the AD. Clear? So here I will name this equation as equation number 1. Similarly, if you observe force acting on AD, so how to evaluate that point? Force acting on plane AD due to shear stress tau. So that will be equal to tau into AD into A, oh sorry, 1. So this is area of AD as A is unit thickness. Similarly, I can evaluate force acting on BC. So here I will consider BC. Clear? So that will be equal to again shear stress into area. Area is BC into 1. Now if you observe this particular equation, then this shear stress is equal again AD and BC. If you observe this length AD and this length BC, both are similar. So I can say that again two forces are acting. So this force is in downward direction, this force is in upward direction. So when two forces having same intensity and opposite nature, it will again form a couple. So due to these two forces, I will evaluate the moment of couple. So here I will consider first force acting on AD, that is tau into AD into, now here we consider the distance. So distance between these two forces, force acting on AD and force acting on BC. So this distance is AB. So here I will multiply the distance AB. So if you look at equation number 1 and equation number 2, then I can conclude that this tau dash into AB into AD, that is equal to tau into AD into AB. Here AB and AB get cancelled, AD and AD get cancelled. So from this derivation or principle of complementary shear stress, I can say that this tau dash, it is equal to the tau. So this is known as a principle of complementary shear stress. In previous case, what we have learned, if you recall it, then here stresses acting on x direction, so that is sigma x, and stresses, normal stresses acting on this direction, so that is sigma y. So these two stresses were different. However, if you observe the shear stresses acting on any plane, if you observe this tau shear stress, that will be equal to tau dash. It is because of the principle of complementary shear stress, and it is always towards the corner or away from the corner. If you show towards this corner B, then here we must consider towards corner D. Clear? And away from A corner, away from C corner. Clear? So this is what a principle of complementary shear stress. Why we have explained this principle of complementary shear stress? Because here we are going to use same principle. So let's start today's discussion, that is on principal stresses on a member subjected to simple shear stress. So here again I will consider shear stress tau. This is shear stress again tau. Now why I am considering only tau? Because as we know, tau dash and tau are equal. So I am considering only tau. So force acting on this plane is also tau. On this particular is also tau. So member is our A, B, C, D. As we need to evaluate the principal plane, so here I will draw another plane. So angle between the plane and this normal plane is theta. So here I will consider the point F. Now here we need to evaluate the principal plane and principal stresses, maximum shear stress and maximum normal shear stress. So let's understand one by one. So force acting on this particular plane BC. So I will first evaluate the force acting on plane BC. Clear? So let's write shear force on BC. So that will be equal to tau into area, that is BC into 1. So that will be equal to tau into BC. Now we are going to consider this segment only. Which one? This CBF, and it is having unit thickness. Clear? So this is our discussion, point of discussion on this particular segment. Now here we have considered the area, this one. I will show you. So here I have considered the area, this BC, as it's having unit thickness. So BC into 1. Similarly, we can evaluate shear force acting on plane FB. So shear force acting on FB, that is again equal to tau into FB into 1. So that is equal to tau into FB. Simple. Now next thing is we need to evaluate. Now this shear forces is going to act parallel to this particular force. Clear? So here what we evaluate, so let's say this is Q1 and this force acting on FB is Q2. Now we want total normal force acting on this particular plane FC. So let's see how the forces are acting. So this plane is FC. Now this Q1 is acting in downward direction. So this is force Q1 which is acting on plane BC. So as we know this is theta, so definitely this will become theta. Clear? Now we can evaluate the normal stress due to this Q1 and tangential stress which is acting along this particular plane FC. So this is Q1. Definitely this will become Q1 cos of theta and this will become Q1 sin of theta. Simple, as this is Q1. Force is acting on BC. Similarly for Q2 force, as you observe, this is C, this is F, and this is force Q2. Simple. Now normal, if I draw a diagram, so this is nothing but sigma n normal force, and here you will get the theta angle. Clear? So sigma n, that will be the Q2 into cos of theta, and in upward direction there will be tangential force due to the Q2, that will be the Q2 into sin of theta. Simple. So you might thinking how this angle become theta. It's just a simple trigonometry. If you consider this as theta, then we can get easily this angle equal to theta. So I will show you how this angle become theta. So this angle is theta. Simple. So if you consider this is normal stress and this is Q. Now if you observe, this one is 90 degree, this vertical line, and this Q2 horizontal line, and as this is theta, this must be equal to 90 minus theta. Again this FC plane and this normal component, it is again 90 degree. So I will show you with the red. Clear? So here I want to show this one, this angle between FC and sigma n, it is 90 degree. As this is 90 minus theta, obviously this will become theta. So here I have considered the angle theta. Simple. So this is a simple explanation how it comes to theta. I hope you understand the angle between the Q2 and sigma n. Now here we need to combine this Q2 and Q1 shear forces in one direction. So here I will write the total. So here I will write total normal force on section FC. So due to Q1, this Q1 sin theta, due to Q2, Q2 cos theta. So here it will be equal to Pn equal to Q1 into sin theta plus Q2 into cos of theta. So what is Q1? Q1 is equal to tau into BC. So here I will write tau into BC into sin theta plus Q2. So instead of Q2, I will write the value of Q2. So Q2 value is tau into FB. So tau into FB into cos of theta. So this is equation number 1. Clear? Similarly, total tangential force on section B. So that is denoted by PT. So due to this Q1, it is in downward direction, and due to Q2, it is in upward direction. So I can write as it is going upward. So Q2 into sin theta minus Q1 into cos of theta. Again I will put Q2 value. So Q2 value is tau into FB. So tau into FB into sin theta minus tau into BC into cos of theta. So this is equation number 2. Simple. So here we can get, so we have evaluated the total normal force and total tangential force acting on section FC. So this is section FC. Now it's easy to evaluate the another stress. So how to evaluate this sigma n? That is simple. Force acting normal on FC plane and the area is FC into 1. So here from equation 1 I can write, so from this equation I can write that tau into BC into sin theta plus tau into FB into cos of theta divided by whole divided by FC. So here we need to understand simple trigonometry as we have already learned in previous also. So this BC divided by FC क्या मिलेगा आपको? That will be the cos theta equal to BC divided by FC. Simple. So here tau into BC divided by FC. So here I will write cos theta into sin theta plus FB. So this is FB divided by FC. So that is nothing but sin theta. Sin theta equal to FB divided by FC. So tau into sin theta into cos of theta. Simple. So here this all terms are common, so I can write 2 tau into sine theta into cos theta. So for 2 sine theta cos theta, we have equation that is sigma n equal to tau into sine of 2 theta, because sine of 2 theta that is equal to 2 sine theta cos theta. So from this equation we get the final result, that is normal stress acting on FC plane is equal to sigma n is equal to tau into sine of 2 theta. Similarly, we can evaluate for tangential stress also. So that is equal to PT divided by area FC into 1. So from equation 2, so from this equation I can rewrite this equation over here, tau into FB into sine theta minus tau into BC into cos of theta divided by FC. So similarly, FB divided by FC, what we have written? Sine theta. So similarly, I will write tau into sine theta minus tau into BC divided by FC. So BC divided by FC, here what we written? Cos theta. So here I will write cos theta into cos theta. So this equation becomes tau into sine square theta minus tau into cos square theta. So if I take minus tau common, then I can write cos square theta minus sin square theta, and from this I can write by using trigonometry terms minus tau into cos of 2 theta. So cos of 2 theta that will be equal to cos square theta minus sin theta. So this is the final expression, that is equation number 4. So from this we can evaluate or calculate the normal stresses and tangential stresses acting on a plane, and from this you can evaluate the normal and tangential stresses acting on this plane FC. Now when we look back, previous video we learned when two mutually perpendicular stresses acting on a body, then we evaluate the forces. So this was the case. Here we considered a bar having unit thickness, and when we apply the stresses along x direction, that is sigma x, along y direction, that is sigma y, the stresses acting on a body, like stresses acting on a body, two mutually perpendicular plane at a right angle, that is sigma x and sigma y, and we evaluate the normal stresses and tangential stresses acting on principal plane. So let's say that plane is A, B, C, D. This is a bar, and plane CF at an angle theta measuring from this plane BC. Clear? So from this we evaluate a formula for this principal stresses and shear stresses or tangential stresses, that is sigma n, that was sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta, and tangential stress was sigma x minus sigma y divided by 2 into sine of 2 theta. So these were the result in previous video. I have explained how it comes. So I will write equation number 5 and equation number 6. Now what I will add in same equation, if you consider a member subjected to like direct stresses in two mutually perpendicular direction accompanied by a simple shear stress. So these were the condition in which if I add shear stresses tau acting on a body, so if I consider these shear stresses, so what I am doing, I am just combining the two cases. Clear? So this case was the member subjected to simple shear stress, and this previously two mutually perpendicular stresses. Now if you combine, then if you just combine result of these two, then we get the final equation. So instead of deriving entire expression, if you derive, then you will get same result. Clear? So instead of that, I will just write from equation number 5 and equation number 3. So this is equation number 3 and equation number 5. So if this is the case, which one? When a member is subjected to like direct stresses in two mutually perpendicular direction accomplished by a simple shear stress. So this is the case. Here if you observe, these are the two stresses, that is sigma x and sigma y, that is direct stresses, like direct stresses acting on this particular body member ABCD in mutually perpendicular direction, and a simple shear stress, that is tau, is acting on this particular body. So whenever you want to evaluate the normal forces acting on this, then just combining the two result. So that is sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta. Here I am just adding the result of this particular case, third case. So that is plus tau into sine of 2 theta. So this is final result 7 number. And if you look after the tangential stresses, that is equal to sigma x minus sigma y divided by 2 into sine of 2 theta. Here I will write this result minus tau into cos of 2 theta. So this is equation number 8. So these are the very important results we got from the derivation. Now let's see the position of principal plane. So here we are interested in position of principal plane. Okay, so when we want a principal stresses or plane, in that case what is the condition? Condition is that shear stresses, that is sigma t, must be equal to 0. Clear? So this is very important. What is principal stress? A stress in which normal stresses should be present and shear stress must be equal to 0. What is principal plane? A plane on which only normal stresses must be act, shear stress must be equal to 0. So from this equation number 8, I can write sigma x minus sigma y divided by 2 into sine of 2 theta minus tau into cos of 2 theta must be equal to 0. So I will shift this term in that direction, in that side. So sigma x minus sigma y divided by 2 into sine of 2 theta equal to tau into cos of 2 theta. Simple. So it's just a simple basic derivation here we are observing. So sine theta divided by cos theta I will consider in this side. So I will write sine of 2 theta divided by cos of 2 theta, then tau divided by, so here I am multiplying this 2 in that side, so 2 tau divided by sigma x minus sigma y. As we all know, sin 2 theta divided by cos 2 theta, that will become tan of 2 theta equal to 2 tau divided by sigma x minus sigma y. Clear? So from this I can draw a simple diagram. A simple trigonometry diagram. Here if I considered the 2 theta, then this side will become sigma x minus sigma y and this side will become tau. So what I need this hypotenuse. Clear? So if you want to evaluate the diagonal, then I can write diagonal as it is right angle triangle. Clear? So I can write diagonal, that is plus and minus under root of this base side and under root of side square, base square and height square. So sigma x minus sigma y, that is square, plus 2 tau square, that is equal to 4 tau square, because 2 tau bracket square, so that will be equal to 4 tau square. Simple. So here I got the diagonal, so that is plus or minus under root of sigma x minus sigma y square plus 4 tau square. Why I am evaluating this? As in this normal shear stress, if you observe, there are two terms are there, cos of 2 theta and sin of 2 theta. I want to evaluate these two value. Clear? So as now I know the diagonal, I can get easily sin 2 theta and cos 2 theta. So from this diagram I can write sin of 2 theta, that will be equal to, in front of side, that is 2 tau divided by hypotenuse or diagonal, it is equal to sigma x minus sigma y square plus 4 tau square. Similarly, cos 2 theta, cos of 2 theta, that is equal to this adjacent side, that is sigma x minus sigma y divided by under root of sigma x minus sigma y square plus 4 tau square. Now by putting these two values, sin 2 theta and cos 2 theta, because we want principal stress, and principal stress it is getting from the normal stress, by putting the value where the shear stress is equal to 0. जहाँ पे shear stress 0 होता है वहीं आपका normal stress रहता है, जहाँ पे shear stress 0 होगा उस normal stress को हम क्या बोलेंगे, principal stress बोलेंगे. So in this equation we want to evaluate cos 2 theta and sin 2 theta. From this diagram we evaluate the sin 2 theta and cos 2 theta. So I am just rewriting equation number 7, that is normal stresses acting on the body. Clear? So here I will write sigma n, that is equal to sigma x plus sigma y, just rewriting this equation, plus sigma x minus sigma y divided by 2 into cos of 2 theta. So here cos of 2 theta, instead of that I am writing this equation. So here I am writing sigma x minus sigma y, I will make it bracket so it will be easy, under root of sigma x minus sigma y whole square plus 4 tau square. Now it is not ended, plus tau into sin 2 theta, so plus tau into sin of 2 theta matlab this one, so 2 tau divided by under root of sigma x minus sigma y square plus 4 tau square. Simple. So we will just simplify this equation. So here again I am writing sigma x plus sigma y divided by 2 plus, here if you observe, sigma x minus sigma y, again sigma x minus sigma y. So a into a square. So likely sigma x minus sigma y whole square divided by 2 into under root of sigma x minus sigma y. I am just rewriting the term plus, here again tau into tau, 2 tau square divided by sigma x minus sigma y square plus 4 tau square. Clear? Now if you observe from these two equation, I am just taking, so here look for these two, I am taking common under root of this equation sigma x minus sigma y square plus 4 tau square. So this one sigma x plus sigma y, I am just rewriting again sigma x plus sigma y divided by 2 plus I am taking this common 2 under root of sigma x minus sigma y square plus 4 tau square. So I am taking this common, so here I will get the same thing, that is sigma x minus sigma y square. Now here 2 is absent, so here I will multiply by 2, so 2 into 2 4 tau square. Clear? The remaining things it will be same. Now here if you observe, it's a 1 by 2, same thing in under root. Clear? So here if you observe a, under root of a, its result will be under root of a, because I can write this a root of a into root of a divided by root of a. So this will get cancelled and you will get under root of a. So similarly I can write sigma n, that will be equal to sigma x plus sigma y divided by 2 plus 1 by 2. So this 1 by 2 I am taking common, and sorry I am taking same 1 by 2, then in bracket I will get sigma x minus sigma y square plus 4 tau square. And if you take 2 inside, then I will get another result, that is normal or principal stress acting on that oblique plane FC, that will be equal to sigma x plus sigma y divided by 2. Here I am writing plus, in bracket I am taking 2 inside, so here I will get sigma x minus sigma y divided by 2 whole square plus, when you take 2 inside, then it will become 4, 4 divided by 4 it will get cancelled, so this will be equal to tau square. So this is, and final result I come out for the principal stresses acting on this particular body when two mutually direct normal stresses are acting along with a simple shear stress. So this is what we got the result. Now if you observe, this diagonal was plus or minus, so everywhere I just forgot to mention this is plus or minus, again this is plus or minus, again this is plus or minus. So here I can rewrite this one plus or minus under root of this entire equation. Now in previous lecture also I just mentioned there are two types of principal stresses are there, major principal stress and minor principal stress. So I can evaluate from this equation, if I take plus sign, so sigma x plus sigma y divided by 2 plus under root of sigma x minus sigma y divided by 2 whole square plus tau square, then this will become a major principal stress. Now what about minor? Just you need to consider sigma x plus sigma y divided by 2 minus under root of sigma x minus sigma y divided by 2 whole square plus tau square. So this will become a minor principal stress. Now these two principal stresses are normal stresses are acting at right angle. So what will be the location? So I will just redraw the diagram. So if I consider the same bar, clear? So this is A, this is an A, B, C and D, and on this plane, if I consider the plane FC, then here I can redraw the diagram. So major principal at this angle theta, the major location of major principal stress is over here. Major principal stress will act over here and minor principal stress will act on this plane. So this will be the minor principal stress and this will be the major principal stress, and location will be at theta, and location of this particular minor stress, it will be theta plus 2. If I measure, sorry, so if I consider this theta, then this angle it will be theta 1 plus 90 degree. So this is all about the major principal stress and minor principal stress acting on a member when two mutually perpendicular direct stresses and simple stress shear stress is acting. I hope you understood the concept. Now next is maximum. Simple concept is there, that is maximum shear stress. So we need to evaluate the maximum shear stress. So we have two formula, that is normal stress. From this we got the principal stresses major and minor, and again we have this equation sigma t, that is shear stress. So what we want maximum. So in that case what we can do, we can take a derivative of that equation. So simply if you take derivative, that is d divided by d theta into tau, if equal to 0, then we can get the maximum shear stress. So let's rewrite the same equation, d divided by d theta in bracket sigma x minus sigma y divided by 2 into sine of 2 theta minus tau into cos of 2 theta equal to 0. What is this equation is for shear stresses. So same equation I have just taken. Now let's take a derivative of this form. So for this first term I can rewrite sigma x minus sigma y divided by 2 into sine 2 theta, derivative is cos of 2 theta, and from this again you need to multiply by 2. So 2 theta over here I have taken 2 minus tau into here derivative of cos theta 2 theta is minus sine of 2 theta, again we need to multiply by 2, so it is equal to 0. So here 2 and 2 get cancelled and minus it will get plus. So I can rewrite sigma x minus sigma y into cos of 2 theta plus 2 tau into sine of 2 theta, that is equal to 0. So again I will simplify 2 tau into sine of 2 theta, that is equal to sigma x minus sigma y. So this is an minus into cos of theta. So this first term I am taking that side. Clear? So if I take this term in this side, then I can write sine of 2 theta. I am taking cos 2 theta. Sorry, this is cos 2 theta. Cos 2 theta over here, cos 2 theta equal to, so this I am rewriting, that is sigma y minus sigma x. I am taking positive, that's why I am taking sigma y minus sigma x divided by 2 tau. So I can write this 2 theta equal to sigma y divided by, sorry, sigma y minus sigma x divided by 2 tau. Similarly, what I want sin theta and cos theta value, sin 2 theta value and cos 2 theta value. So I can draw a triangle from tan 2 theta. So if I consider this is a 2 theta and if I consider this is a right angle, then I can write this is in front of side, that is sigma y minus sigma x, and this side will become tau. So what will be the diagonal? So we can get under root of sigma y minus sigma x square plus 2 tau square, that is 4 tau square. Simple. And if you get this diagonal, so you can easily write for sine 2 theta. So if I write sine 2 theta from this equation, then this will be the sigma y minus sigma x divided by diagonal. So I will rewrite sigma y minus sigma x divided by, so again this is plus and minus, remember, sigma y minus sigma x whole square plus 4 tau square. Similarly for cos of 2 theta, so cos of 2 theta, that will be equal to 2 tau divided by diagonal, 2 tau, again this is plus or minus, your diagonal is sigma y minus sigma x whole square plus 4 tau square. So what we want to do, just put this value sine of 2 theta and cos of 2 theta in equation of shear stress, that is sigma t. Clear? So if you put sine of 2 theta and cos of 2 theta, then we get the equation. Simple. So I will rewrite that equation, that is tau max, sigma tau max, that will be equal to sigma x minus sigma y divided by 2 into sine of 2 theta. Instead of that, I will write this equation sigma y minus sigma x divided by under root of sigma y minus sigma x whole square plus 4 tau square. Again plus or minus, this is again plus or minus. Clear? This term is plus or minus, but it is in multiple vector. So 2 tau divided by under root of sigma y minus sigma x whole square plus 4 tau square. Simple. So if I take minus as a common, because this is a plus or minus, so you can rewrite like this also. So I can write sigma x minus sigma y whole square divided by 2 into under root of sigma y minus sigma x whole square plus 4 tau square plus or minus again 2 tau divided by under root of sigma y minus sigma x whole square plus 4 tau square. Again I am taking 2 under root of sigma y minus sigma x whole square plus tau square common. So here I will get, if I take 2 under root of sigma y minus sigma x whole square plus 4 tau square, then this term as it is, that is sigma x minus sigma y whole square plus, here 2 is missing, so I will multiply over here, that will become tau 4 tau square. Clear? So 4 tau square. Now one thing is missing. Wait, let me check. Yes, missing is here. So here equation is tau into cos of 2 theta. So what we missed? We missed the tau. Clear? Into tau. So this will become 2 tau square, and that's why here I will get the 4 tau square. Simple. Because equation, if you observe, this is tau into cos of 2 theta. So tau into cos of 2 theta. So here I will get 4t square. Again both are similar thing, because this is again plus or minus. Simple. So if you take similarly, that is a divided by under root of a, so that is I can write a under root of a into under root of a divided by under root of a, so it will get cancelled. I will get only under root of a, so that is sigma t max. I can write 1 by 2 under root of sigma x minus sigma y whole square 4 tau square. Here if you observe over here, when you write sigma x minus sigma y, it will be negative. Negative square, that will become positive. So you can write either way. So if you write sigma x minus sigma y whole square, that will be equal to sigma y minus sigma x whole square. क्योंकि यहाँ पे नेगेटिव भी आता है तो उसका हम क्या लेने वाले, स्क्वायर लेने वाले. So instead of that I am writing sigma x minus sigma y. So here you will get the maximum shear stress acting on the body. Clear? So you might get a lengthy lecture, but this is a very important lecture as per principal stresses and strain is concerned. So if you want to locate the principal stresses and strain inside the body, then I can say that in previous video we may observe that this angle was theta 1 plus 45 degree. So 45 degree, at 45 degree we get the maximum shear stress. So here again I can redraw the shear stress plane. So here maximum shear stress, it will act on this particular plane. Clear? So this will be the maximum position of maximum principal shear stress. So sorry, it's not principal, maximum shear stress value. Clear? So not only at 45 degree only, again here if you observe we get at theta 1 plus 135 degree. So here how this 45 and 135 came into picture, for that purpose you need to look or observe my previous lecture. I hope you understand the concept of principal stresses and plane and its position, principle of complementary shear stress also. So on this particular topic we derived entire topic. Now whatever the numericals are there, we will see in next lecture. So till that, thank you so much.